All right, let me take a look at something called Simpsons rule. Here we'll kind of justify what it's about and then kind of go through the process here. See if I can remember it from scratch. So the idea is, and we're still in our numerical methods for estimating the area under a curve, okay, which is our picture of definite integral. We know that it doesn't always mean exactly area, but since it's under a curve, everything that we've done so far to estimate has had flat sides, whether it's a trapezoids or rectangles, and it really would make sense that we're probably never really going to have flat pieces on that. So if even if we're working off of data, we could make that curve on the top of the thing, then we would probably get a better answer. Okay? So our simplest curve is a quadratic. Right? Our quadratics that look like y equals ax squared plus bx plus c. It takes 3 points to determine where a quadratic is. So if, and we'll go ahead and center this around the origin because side to side shifts overall are not really going to change what the area under here is. But if we take a look at these 3 points, and we'll call this a point negative h comma, we've got some y value out of there, we'll call it y0, and we've got a point at 0 comma y1, and a point over here at h comma y2. And so with those 3 points, we should be able to fit a parabola through there. It may not exactly match what's happening with the curve, but it should do better than the straight line thing did. And then if we were to be able to find the area under that, then that should give us an even better estimate. Okay? So if we knew that this was the equation, then our question is, what is the definite integral from negative h to h of ax squared plus bx plus c dx? And we know now that that's the capital F of b minus capital F of a, where capital F is some antiderivative of this. And the antiderivative of that would look like 1/3 ax cubed plus a half bx squared plus cx. You can double check that. Take the derivative of that. You'll see that we get ax squared plus bx plus c, and we need to evaluate that from negative h to h. So when we put an h in, we get a 1/3 a times h cubed plus a 1/2 bh squared plus a ch, and then we'll subtract, and that'll come out to be a negative 1/3 ah cubed plus a half bh squared. The squaring ignores the negative, minus cx. And so putting all of this stuff together, I get 2/3 ah cubed. The half bh squareds cancel each other out, and this should be a ch minus the negative ch gives me 2 ch's. Okay? And so what I see right now, having worked this all out, is I don't even need to figure out what the b is. Okay, the b is not even involved in this formula right there. If I could figure out what the a and the c were, still feels a little bit like a daunting task to have to do this if I'm making a bunch of these little parabola-topped areas. Okay. Well, how would we go about finding what the a and the c are? Well, that's where we use these points. Okay, so the points that we have, if we plug them into this equation, we get one equation that says y0 is going to be what I get if I plug a negative h in there, which is going to be ah squared minus bh plus c. Y1 is what I get if I put a 0 in for all the x's. That's just going to be c. And y2, if I put a negative h in, is going to be, or a positive h, ah squared plus bh plus c. Um, okay, I see this AH squared here. Okay. And in fact, if I do y0 plus y2, I would get 2AH squareds. The BH's would cancel out and I would get plus 2C. And so if I compare these two things, okay, well, I could get an h squared if I factored an h out of this top one. So let's take a look at this top one and see if we can make a 2ah squared show up. And I think we could if we factored out an h over 3. So if we factor an h over 3 out of that, that would leave me with a 2ah squared. You can check as if we multiplied that back in, we'd get that. The question is, what are we left with then? Well, we pulled the h out. We pulled out a 3 of the denominator that wasn't there, so that needs to multiply on it, and that's going to give us 6 c's. Okay, so comparing this with this, we got the 2ah squared plus 2 c's. I'm missing 4 c's. If I could find 4 more c's, I would be able to make a substitution here. Okay. And remember that this is my answer that I'm looking for here. So, well, I've got this. Okay, the y1 is equal to a c. So what if I added on 4 of the y1s? That would add on 4 c's, and this would give me y0 plus 4 y1s plus a y2 is 2ah squared plus 6 c's, and that matches what is in there. And then I can make a substitution and replace the 2ah squared in this. I'll keep the h over 3, but now inside the parentheses, instead of 2ah squared plus 6c, I'll use its new name, which is y0 plus 4y1 plus y2. Okay, and so the question is why? Why is this better than anything else that I've had up to this point? And the answer, if you look at it, is that there is no A's, B's, or C's in this thing anymore. Okay, the only things that I need to know is how big is the gaps, okay, which is something I probably get to choose along the way here. I need equal size gaps. And so if I have equal size gaps, this is definitely not a Riemann sum. This is not making rectangles. Okay, the trapezoid rule was not a Riemann sum because it didn't make rectangles. But all I need to know for this is the size of the gap and the y values of the 3 consecutive points. So this formula that's in the black square here figures out what the equation of the parabola is, does the definite integral of it from negative h to h, and gives us what that answer is, does the capital F of B minus capital F of A for us, and all of that in a single step. Okay, so what do I need to have this happen? Well, I need to know 3 consecutive y values. When I was doing my Riemann sums or my trapezoid rule, they needed to come, I just needed 2 numbers. But since it takes 3 numbers to determine a parabola, I'm going to need 3 numbers going for me here. Okay, and that's represented by the y0, the y1, and the y2. And you'll also notice that it doesn't matter anymore the way where I centered this thing. It just has to do with what the y values are. Okay, and all that matters is the gaps are of an equal size. The divided by 3 was a result of the math that I did. So if I'm trying to memorize what's going on here, I'm just going to have to remember that it is the width of the interval divided by 3 when I'm doing Simpsons rule. Maybe I remember that because it takes 3 points to do that. But I always am going to need an even number of data points, or split into an even number of intervals. Okay. Otherwise, I'm going to be left with something hanging out here at the end. All right, so let's take a look at what happens if we're stringing more of these things together. So let's go ahead and label these points just as an example. Let's say these data points were in there every 7 units. So 7, 14, 21, 28, 35, and 42. And what Simpsons rule is going to do is it's going to take these first 3, and it's going to say that's the parabola, and I'm going to find the area there. And then it's going to look at that next set of points and say, okay, that parabola maybe has that equation, and it's going to find that area. And then finally, it's going to look and say, okay, that one looks more like that. Okay. And it's going to find that area, and we're going to add those together. Now, do I believe that that's what the function looks like? Probably not exactly. That corner point at 14 is unlikely, but it should do a better job than my other things. Trapezoid rule looks like it probably wouldn't be too bad on this at all. So let's make some numbers up and actually go through this thing. So let's say this is at the point, we'll call that 9. I'm just going to list y values on these points here right now. I'll say that's 12. They'll make this maybe a 7. This looks like it's right around where that 9 was as well. We'll call that a 15. We'll call that an 18 and a 17. Okay. So what I'm going to need here is, as I look at these as y0s, y1s, and y2s, it's these points in the middle that I needed 4 of each of those. So to do the green arrow, it was the width of the interval, which is 7, divided by 3 because it's Simpsons rule, and then it is the first y value plus 4 of the second y value plus the last y value. So I probably should have done that one in green to match there. That's 9 plus 4 times 12 plus 7. There is my first one, and then I'm going to add on to that my second one in blue, which again is 7 over 3 widths of the intervals, and I'm going to need the 7 plus 4 times the 9 plus the 15, and then I will add on to that the red one, which still has the 7 over 3 width of the interval divided by 3, and I'm going to need the 15 and 4 of the 18s and the 17. Okay, and if I were to look at this all strung together, I mean, I certainly could do these calculations, but I see that they all have the 7/3 in common, so I could factor out the 7/3, and what I would have left on the inside, I've got a 9 plus 4 of the 12s plus a 7, and then I've got plus a 7 plus 4 of the other 9s plus a 15 plus the 15 plus 4 of the 18s plus the 17. And I can see that the 7, which was this 7 back here, got used once as the end of the first parabola and once as the beginning of the second parabola. And the same thing happened with this 15. So the 9 is only going to get used once. The very first point gets used once. The 17 at the end gets used only once. And so I could rewrite this whole thing as 7/3 times 9 plus 4 of the 12s plus 2 of the 7s plus 4 of the 9s plus 2 of the 15s plus 4 of the 18s plus the 17. And I can see this pattern of 1 times there, 4 times, 2 times, 4 times, 2 times, 4 times, and then finish with 1 time right there. So this 1, 4, 2, 4, 2, 4, 2, 4, 1 kind of pattern, that's characteristic of what we do with Simpsons rule. So I guess we might as well come up with a final answer for this. Let's see, that's 9 and 48 and 14 and 36 and 30, and did I miss something along the way? I thought I did. Nope, I didn't. Plus 30 plus 4 times 18, 40, 32, 72, plus 17. 9 plus 48 is 57, 67, 71, 107, 137, 209, 226, I think is what those add up to. Which is not divisible by 3, but is, and certainly multiply things by 7 there, and we'll get an approximation. 7 times 226, and divided by 3, we're going to say that's about 527.3 is our approximation for the area under the curve given by those points. Now, if I actually had a function that I could generate actual function values, I would be able to check and see how close Simpsons rule gets. I can tell you that Simpsons rule is programmed into the calculator, so it does as many intervals as its pixels will allow. But you can also write a Simpsons rule program. It would probably be based on the other one. I don't know if you could pull it off in exactly the same program or not. Somebody could probably figure out how to do that. But that is the idea of Simpsons rule. Because it does make parabolas on top of there, it means if you are estimating the area of something that is quadratic in the first place, it will nail it exactly. Because it perfectly would fit that curve all along the way. So that is it for Simpsons rule.